On to our final speaker of the session, who is Matthew Lightfoot. So Matt is the editorial team leader here at CCDC and is also the product owner for our internal systems that we use to create the CSD. Matt did a PhD in Manchester before joining us, and he celebrated his 20th anniversary at the centre this year. So he's been pivotal in evolving how we process data into the CSD, and today he'll be talking about the challenges and impact of data curation and the power of the CSD. So over to you, Matt.
Thanks, Suze, and welcome everyone to today's CCDC UGM. Today I'm going to talk about some of the challenges we have had and are currently having with data curation and how we'll look to solve these challenges. So I'll start by giving a brief introduction to the CSD. I'll then talk a bit about how we create the CSD, and I'll describe some of the challenges we've had and are having in the area of data curation. I'll conclude by talking about some of the recent initiatives in the data team and how these have positively impacted the data and hopefully the users of the data. So as a lot of you will be aware, the Cambridge Structural Database, or CSD, reached 1 million structures in 2019, and the database continues to grow in size and should reach 1.1 million in the next few months. The CSD contains every small molecule crystal structure published in the literature and includes patents, theses, and structures published in university repositories. You saw this slide earlier from Jürgen, and the CSD contains a mix of organic and metal organic structures with a split between multi and single component complexes. And the CSD is used in a variety of industries and includes metal organic frameworks, which is an area that has grown significantly over the last 10 years. Not only does the CSD contain structural data for over 1 million structures, but we also have a significant amount. Oh, it's moved on. A significant amount of additional data, including melting points, bioactivity data, and oxidation states. An important area that we focused on recently is improving the linking between the CSD and other related databases. And I'll talk about this more later in the talk. So now we can move on. So one area we've been looked at recently is demonstrating the depth of data in the CSD. And here's an animation showing how the number of structures containing different elements has increased over time. And you see the number of structures containing phosphorus has grown a lot in the early 2000s, and fluorine expanded a lot in the kind of late 2000s, the 2010. So now I'll spend a few minutes talking about how we create and curate the data in the CSD. So creating the CSD is not a simple effort or a one-time event. So every data set undergoes a series of steps in the curation process. And as you'll see from this workflow here, it's quite a process. So the steps in green are automated, and the steps in red require some manual intervention, either internally or from external depositors or publishers. And we have two teams of scientists who assist in this process. When a data set is first deposited with the CCDC, a team of deposition coordinators, they triage the structures and work to fix any errors in the files. And then once the structures are ready for curation, so once they're published or they're published directly through the CSD, then our team of editors curate the structures so they assign chemistry and other meaningful metadata to the entry. And I'll talk a bit about this more in a few minutes. So to help with the process, we have a web-based deposition process, which allows users to deposit their structures using a 7-stage process, which allows depositors to validate and enhance their data sets. And the process includes steps where the data sets are syntax checked and run through the IUCR's checksys service. And at the final stage, depositors are encouraged to add any missing metadata that is important for enriching the data set and the CSD entry. And the deposition process is now used to deposit structures for inclusion in the CSD and the ICSD. So to create the CSD entries, we use the existing data in the CSD to help us automatically assign the chemical connectivity to the new structures as they enter the database. And to do this, we use a tool called Decipher for this. And this was developed at CCDC by a team led by Robin Taylor, our keynote speaker earlier today. So Decipher uses a probabilistic approach, taking into account the geometries and likelihood of occurrence in the CSD, and it uses a Bayes theorem. So this takes the coordinates and produces the most likely chemical connectivity for the structure. As I said, Decipher is a key part of the process of creating CSD entries, and this includes a number of steps, including resolving disorder and identifying polymer units. And once the chemical connectivity has been calculated, we then generate a chemical diagram and a chemical name. But a key part of the process before an entry is finally added to the CSD is that it's manually reviewed and validated by our expert editorial team, and this is every structure. So automation is an important part of the process, and it allows us to focus our editorial time on the most important parts of the validation process, so that we can make the data as useful as possible for our users. So here are a few examples in which our manual work is important to ensure the quality and the consistency of the data in the CSD. So the diagrams show that the before and after the manual work, and that it was required to correct the chemistry and clean up the chemical diagrams. So I'll now let's talk about some of the challenges that we have and we're currently facing in data curation. So here are 6 of the challenges that we believe are currently important for us to focus on, and include complexity, quality, data integrity, emerging techniques, consistency of metadata, and interoperability. And I'll cover these at various points in the remainder of the presentation. Now we can see over the years that the diversity and complexity of the CSD has increased. So here you can see in these 2 graphs that you can see the increase in complexity demonstrated by the increase in formula weight and cell volume. And this creates challenges for data curation, as our automation methods can have issues with larger and more diverse structures. So this puts more emphasis on the manual validation and curation processes that are completed by our editorial team. And to deal with this, we have to consistently review how we spend our time to make sure we're focusing on the main areas, so we can ensure that we're providing the maximum value to our users. And as you can see, as this research develops and new chemical insights are found, then the CSD continues to become more diverse, both chemically and crystallographically. And it's important that we stay on top of these new developments in chemistry, so that we can ensure that all structures are represented correctly in the CSD. So on this slide, I've highlighted 4 areas which can cause particular challenges during data curation. Missing hydrogen atoms and poor geometry of structures can cause problems interpreting the chemistry. And this can be quite time consuming and can involve investigating both the original publication and sometimes requires correspondence with the depositors of the structures. Another area which can be problematic is interpreting the oxidation state in the complex. Again, this can be time consuming and often involves checking the original publication. And finally, another area which causes us a lot of problems is when disordered molecules, often solvent molecules, are removed from the structure using a squeeze, mask, or a similar procedure. And often there is very little information in the deposited data about the identity of the removed molecules. So again, this requires quite a lot of manual investigation. So as I mentioned earlier, the complexity of structures is increasing as techniques and programs advance. And as the complexity increases, then this can cause challenges for data curation. So we're now getting larger polymeric structures and larger metal complexes. And there were other examples from Robin earlier. And it can be time consuming to ensure that the chemical representation of these complexes is correct. So larger complexes also result in there being more possibility that there are errors in the data. And when we find errors, and it can be quite a significant amount of manual effort to resolve the problems. Another data curation challenge that I wanted to talk about is how we deal with differences in chemical representation. So the data in the CSD has been added over more than 50 years now, and over that time the representation of structures in the literature and in the CSD has changed. Also, chemistry given by authors is not always consistent with publications and between publications. So we now have a more automated process to help with this, and some structures are represented in a standard way in the CSD. But if there are various ways of representing something in the literature, then there are probably represented with some of these same differences in the CSD. So there are ways of allowing for these inconsistencies when creating searches, and some of the experienced users of the CSD will be aware of techniques they can use to help to search the CSD to get better results. But obviously this can cause problems for new and inexperienced users. So we are looking at what we can do to help with this in the future. And two possible ways that we could help is by providing a standard representation for all structures. And another way is to improve our search algorithms to find all the representations. So kind of like a Google type search for structural chemistry. And as everyone will be aware, an emerging area over the last few years is AI and machine learning. And it's clear in this area that the quality and consistency of the data is really important. And I hope I've showed how we value quality in the CSD highly. And we hope to continue to maintain these high standards in the future. Another way we're looking to improve the value of the data in the CSD is by revisiting subsets of entries. So over the last few years, we've carried out a number of improvement projects, including the consistency of older entries, creating and enhancing subsets of the data, and enriching different types of data. And currently, we're looking at a number of different improvement themes, including improving consistency, prioritizing important industrial relevant data, looking at how we can expand the data in the CSD, looking at how we handle emerging techniques, and increasing the accessibility and availability of data. So here's another animation showing how the metals in the CSD MOF subset have changed over time. So it looks like elements like silver, zinc, cobalt are on the rise, and also lanthanides such as neodymium and gadolinium are starting to appear on the list too. And on the right-hand side of the slide, you can see analysis of the crystal colors in the CSD. You see there's quite a range. So I've now looked at some of the challenges that we have in data curation and some of the activities we are doing to look at these challenges. And I'll now look more widely at some of the recent initiatives in the data team. So one of the areas we have looked at is the integration of different structural databases. So on the slide, the main four structural databases are given with the overlap and the details of some of the collaborations we currently have with these three other databases. One of the recent database integrations has resulted from our collaboration with Fitzcarrasra and the ICSD, and resulted in a development of a joint access and deposition services for organic, metal organic and inorganic structures. So this collaboration has allowed us to implement free access to individual data sets based on all our deposition and access services that we've already developed. And this is good for both communities, and especially the community that work at the boundary of the structures between the ICSD and the CSD. Another important collaboration is with the protein data bank that Alice has just talked about. And this includes including mogul geometry analysis in the deposition process, and also linking between ligands in the PDB and CSD entries. One of the important areas that we've looked at over the last few years is improving the interoperability of the data in the CSD. And to do this, we've looked at how we can link the CSD to other web resources. So we now have links between the CSD and a number of web resources, including the PDB, but also Drug Bank, the PPDB, and PubChem. And this allows our users and users of these other web resources to discover new data and that they potentially could be interested in. And over the next few years, we want to extend linking both between entries in the CSD and to other data resources. We see improved linking has been really important in allowing users to discover new and exciting insights, both from the data in the CSD and from other external data sources. And another important area is linking between the CSD and journal articles. And over the years, we have increased the number of publications that link to CSD entries. So we now have links between CSD entries and the public articles for all the major publishers of crystallographic data. And over the last few months, we've added links between Hindawi publications and the CSD. And in the past week, we've extended the number of ACS journals that have links. So links between CSD and publications are really important. So they allow users of the CSD and the readers of journal articles to discover more about the area they're looking at. Another initiative we have is to ensure that the data is all data is publicly discoverable. So this one of the initiatives we have is CSD communications. So the CSD communications, they enable data that might not otherwise be published to be discoverable by the wider community. And they also provide researchers involved with the credit and recognition. And these have been increasingly popular in recent years and now account for around about 10% of structures that are published annually. Last year, we applied and were awarded Core Trust Seal certification. This is acknowledgement of the work we've done to ensure that we're seen as a trusted repository with a clear data preservation policy, links to publications, and we clearly defined processes all the way from deposition all the way to data access. And as I've described, an important area for us is that we make the data in the CSD as discoverable and reusable as possible, as articulated in the FAIR data principles. And key to this are standard file formats and dictionaries that are developed through the ICR, coupled with the validation services. So this allows compliance, completeness, and consistency of data sets. But these on their own would be nothing without adoption by our key stakeholders, such as the software providers, data repositories such as the CSD, and publishers. Another important area at CCDC is integrity of the data in the CSD. One area I've looked at is data completeness and identifying the steps that we can take to ensure that the data that is deposited is complete, as well as what as quality metrics we could have to allow users to select the data that is fit for their purpose. The second aspect is data consistency. So, for example, looking to see if we're correctly identifying synchrotron data. And lastly, we've been looking at trustworthiness, so to try and establish automated processes to identify potential cases of fraudulent or plagiarized data. Another area we've developed over the last few years is providing different subsets of CSD entries that would be challenging or time-consuming to create manually. So they vary in size from just a few hundred entries to several 100,000 entries. But every entry in the subset is identical to the entry in the CSD. And every time you do a CSD update of your desktop software, the subsets will be regenerated to include the latest data. So these subsets allow you to focus on the structures that most interest you and give you a useful starting point for any further analysis you might want to do. One area that I mentioned earlier on has been a challenge at CCDC is making sure that you're able to handle new techniques, including new methods of data collection, such as electron diffraction, as well as handling new refinement methods. And another emerging technique is crystal structure prediction, where the aim is to go from a 2D representation of a molecule to the prediction of a 3D crystal, of the 3D crystal structures that it could form. And this involves a range of computational methods to predict molecular conformations and their possible packing. And this results in a landscape of plausible crystal structure forms ranked by their energies. So CSP has advanced significantly in recent years, and it's now routinely adopted by industry to inform drug product formulation. but it still remains computationally expensive, however, and thus costly. So industry understandably want to make the most of the data resulting from their investment, and with an increasing number of public and proprietary CSP data sets becoming available, there's need for data management solutions to solve these, and this is an area we are looking at by collaborating with a number of important partners in this area. And this leads us on to our database evolution project, where we're looking to create a new modern platform for storage and searching our data. So this platform will be able to store the current CSD in a more effective way. An important requirement of the project is that it will be extensible, so we can store more data related to the structure, as well as new types of data, including predictive structures and proteins. Finally, I would like to show an example of how you never know when data in a repository such as the CSD might suddenly become important. So on the slide here, we've are two structures that have been identified as possibly having a therapeutic effect against COVID-19. So at the top, there's dexamethasone, which was published over 13 years ago. But we see from our logs that over 57% of views and downloads are from this year. And then on the bottom, there's remdesivir, which was published 3 years ago, and over 99% of views are from this year. As well as looking at trends in the use of data, we've also been watching for any impact COVID-19, the COVID-19 pandemic might have on the flow of data into the CSD. So the number of deposits that we get each month has remained steady, and the totals are comparable, if not slightly higher than the equivalent period last year. But of course, given the typical lag between experiment and publication, it's possible that the impact of reduced access to labs on publication throughput will be delayed. And this is something that we'll continue to monitor over the next few months and years. So to summarize, I hope I've given you an insight into some of the challenges that we have faced in the data team and some of the initiatives we have to deal with some of these challenges. Hope you've seen how curation in the CSD is important so that users can find and analyze the data more efficiently. And there are many opportunities, including ensuring that our validation processes give most value to users, what we can do to improve existing CSD entries, making sure that the data is discoverable as possible and interoperable with other data sources. And finally, how we can extend the data available in CSD entries and also extending the types of data we store. Thanks to the CCDC database team and the many authors who have contributed to the structures in the CSD, and for Olga for her amazing vision. Thanks also for joining the meeting today, and I hope you find the day useful and you're able to gain more understanding of how you can use the data in the CSD more in the future. And thank you for listening, and I'm happy to answer any questions.
Great, thank you very much, Matt, for a really comprehensive talk. I'm conscious that we're running over on time slightly, so if people do want to take a coffee break at this point, Jonathan has put a link to the agenda page on the chat box. At 11:15 we will be going into session 2, and that's 3 different tracks. If you do want to take coffee now, then please do so. If you do have questions for Matt, then Matt will still be here for the coffee break until 11:15 to answer some of the questions. And you have got some questions already, Matt. So you've got one from Laura about recrystallization solvent metadata, and if there's a way that that could be made more machine readable. So I guess there's often different synonyms and chemical names for the same solvent between a variety of different CSD entries. So is that something that we are looking into?
So yes, it is. I mentioned near the end of the talk about the database evolution project, and that currently is looking at how we can store the data in a better, more effective way so that it can be more better read. And how we can then improve that data to make it better both for manual users and for machine readable.
And then you've got a question from Simon Coles at Southampton, talking about as people start to share more data, we're going to have lots of different versions of data. They could share data at every point in the refinement process. I guess that's going to cause challenge in terms of increasing volume, complexity and diversity of structures. And Simon did try and summarise it. I don't know whether you can talk verbally, Simon, or you want me to try and summarise. I think main point was what's the best starting points for dealing with that in the future?
Yeah, I think the essence is that we could bombard you with all sorts of supplementary information, and where would you start with all of that? How would you make sense of it?
So I guess we kind of. I think our new, so once we've got a new database format, then hopefully that gives us a lot more opportunities to the way that how we can store data and how we can add it to CSD entries. I guess we're always interested in how we can look at expanding the CSD and the data in the CSD. So it's definitely something we want to consider more in the future.
And I guess it's going to be important that users aren't bombarded with data. So if they do just want to see one version of a record, they can, but then they can dig a deeper. And I think that we're going to have to radically change how we store data to be able to facilitate that. We've also got a question from Camille.
Yes, can you hear me, Matt?
Yes, thanks.
Oh, excellent.
Yeah.
Thanks for a great talk. My question is about these problematic data hits. I mean, the structures which are obviously wrong, determined in a wrong space group. They're not retracted from the database, right? So they stay in the database. When you do a systematic search and you would like to do a statistical study, can you deactivate them from the statistics, on how you can go on with that?
Yes.
Matt, before you answer, I'm going to have to leave you to answer because I'm going to have to go to the other session, if that's okay. So thanks again for your talk, and I'll leave you to answer the question. Thanks, Camille.
Thanks.
Yeah, this does come up quite a bit with kind of users on kind of because there are obviously over 50 years there have been errors that have been published in the literature. This again, I guess this is another one that we'll kind of once we've got this new format, and hopefully it will allow us to have more flexibility. I mentioned about kind of data integrity and things, and how we can allow people to pick data that's fit for their purpose. So this is probably one of those examples. So when there are errors, you do want to exclude it, don't you? So it's definitely something we want to do better in the future.
Yeah, thanks.
Okay.
I mean, some people just use a kind of well, take for the study the structures with basing on the threshold of the R factor, for example, which can be a kind of solution.
Yeah, I think if structures are retracted in papers, then we would retract them, but it's often I guess structures from quite a number of years ago. So
okay,
yeah,
that makes sense. Thanks.
Okay, thanks.
Matt, thanks so much for your presentation and for the other presenters in this morning.